Welcome to the Chapter 3, Part 3 video. We've looked at exponential functions in Section 1, then we looked at their applications and introducing logistic functions in Section 2, and now we're looking at logarithmic sections in Section 3. These are the three functions that are central to this chapter. So this is the last function that we're going to be introducing here. And a logarithmic function has a very special role in that it is the opposite or inverse of an exponential function. So we're going to look at that relationship and then look at applying it. So in this section, we're going to look at the inverses of exponential functions, and then we'll look at the special cases of common logarithms, which is a base 10. We're going to talk about what that means, and natural logarithms, which is base e. Again, we'll talk about what that means. And then we're going to look at just a brief example of graphing logarithmic functions. Why do we care? Well, logarithmic functions are used in a lot of applications, including the measurement of relative intensity of sounds. So when we are hearing certain sounds, we say that it's a certain number of decibels, and the decibel measurement is an inverse of the exponential function. It's a relative intensity of sound. Other ways that we can see logarithms and exponential functions are things like the Richter scale for earthquakes. So we'll look at a couple of those examples throughout the chapter, but in this section, we're not going to be applying it quite yet. So the first thing that I want to do is look at why logarithmic functions are necessary. So let's look at this function, y equals 5 to the x. And what I want to do is first, I'd like to try to let x equal 4 and find y. So we're going to substitute x to solve for y. So we have that y equals 5 to the x. And since x is 4, we can say that this is 5 to the 4th. 5 to the 4th is 25 times 25, which is 625. Okay, that part we can do. But now let's see what happens when we try to substitute a value for y. So if we want y to equal 12, then we would say 12 equals 5 to the x, and then we're stuck because 12 is not a perfect power of 5. Now, if y equals 25, then we can say 25 is 5 to what power? And then we can say, oh, well, I know that x has to be 2 because 25 is 5 squared. So then x must be 2, right? But if y is not a perfect power of 5, then we're stuck. There's no way to solve for x. And that's where logarithms come in. We have to be able to ask, to what power? Right? I want to solve for the power. And so that's the key question for logarithms. I can say 5 to what power is 12? And the answer is not going to be an integer. Okay, and that's how we can solve questions with logarithms. So let's take a look at logarithms. We need them because we need to be able to solve exponentials, meaning we need to be able to use exponential functions backwards. And we already talked about how inverses, meaning the opposite, are a reflection over the line y equals x. I want to remind you that that is not the x-axis or the y-axis. It is the diagonal line. Okay, y equals x has a slope of 1. We can say it's 1x plus 0. And this is how we can see the relationship of those inverses. The x and the y switch places, right? So this is my exponential function. And this one is what we're going to call a logarithm. And they act in the opposite way. So what does that mean? Well, it means that whatever I do as an input for one is the output for the other. So we can switch between logarithmic and exponential form. Now, there are a couple conditions that we have for this. If x is greater than 0, so the argument has to be positive because remember, we can never have a negative output to an exponential function unless there's some sort of reflection going on, okay? And then our base has to be bigger than 0. We're looking at a positive base because remember when we had a negative base, the function was not continuous. These are things that you saw in that exploration that we did on the first day of chapter 3 before you had even watched the 3.1 video. And the base is not equal to 1 because when the base was 1, it made a straight line. It did not give you an exponential function. Okay, so if we meet those conditions, then y equals log base b of x if and only if base b of raised to the y equals x. So how can we remember this? Well, b to the y equals x. If I take the base and I go around the equal sign, okay, then we can write this as log base b. Always start with the base. And then we past the x, so of x equals pointing to the y. We can do the same thing going backwards. So again, first step is to identify the base, then go around the equal sign. So I can say b raised to the y equals, it's pointing at the x. So we can go back and forth using this method of circling the base and then going around the equal sign. And what we're doing is we're really calculating the inverse function. We are switching the role of the x and y. Okay, so again, this was our exponential form. And this is our logarithmic form. And we can switch back and forth because these are inverses of each other. Okay, so whenever you're solving for something and you're stuck, a good way to get unstuck for exponential and logarithmic forms is to change form. So that's a really good tip for if you're stuck solving for something, you can't isolate it, try switching forms. Okay, so let's look at an example here for properties. And we're going to use a general logarithm with an unknown base. So this is theoretical, base b. Whatever base that is, it has to be positive and not equal to 1. Otherwise, we wouldn't have a logarithmic equation because there's not an exponential equation to take the inverse of. Okay, so if we have log base b of 1 equals 0, well, if I circle the base and I go around, that would give me b to the 0 equals 1. So really what we're doing is we're taking this exponential equation that we know to be true, and we are applying it to the logarithmic form so that we can see some of these logarithmic properties. So we can do the same thing. Anything to the first power is itself. So if I take the base and I go around, that means that log base b of b equals 1. If the bases match, they essentially cancel out to 1. And that means if I have log base b of b to the y, they cancel out, and all I'm left with is y. Okay, we can see that because base b to the y equals base b to the y. So if I circle my base, log base b of b to the y equals y. Okay, so really all we're doing is we're switching back and forth between exponential and logarithmic form, and we're looking at what properties we can kind of solve for. This last one is fun. Again, we're seeing that the bases match, and when the bases match, essentially they cancel out. Okay, so if I take log base b, go around the equal sign, that gives me b to the entire expression, log base b of x equals, what am I pointing at? I'm pointing at x. Okay, so we can say that they essentially, this b to the log base b of x is going to reduce to just x. Okay, so those are some properties of logarithms. We're going to look at these exact same properties applied to special logarithms. And those special logarithms are when we have particular bases. Okay, but first I want to look at this application. So x and y, if I'm looking at my xy, x and y, the inverse should say, okay, then I take y and I give you back x. Okay, so if I'm looking with a base of 2, then I can say 2 to the negative 3 2 to the negative 3 is 1 over 2 cubed, which is 1/8. 2 to the negative 2 is 1/4. 2 to the negative 1 is 1/2. 2 to the 0 is 1. We should see this pattern. We should recognize this from our exponential functions, right? And the logarithm, what we want it to do is take this y value and give us back the x value. So I take 1/8, and essentially we're asking that question again, to what power? So I see my base is 2. I say 2 to what power is 1/8? 2 to what power is 1/8? Well, I know that it's going to be negative because I have a fraction, and 2 to the third power gives me 8. So I got my output of -3. 2 to what power gives me 1/4? Well, again, it's going to be negative because it's a fraction, and 2 squared is 4, so it's going to be -2. 1/4, -2. So notice we're doing all of these backwards. If I take an x, now I'm spitting out the original x. I'm going backwards. The x and the y have switched roles, and that's what makes this an inverse, okay? I can say 2 cubed is 8. Well, now I'm saying log base 2 of 8 equals 3. 2 to what power is 8? 3. The power has to be 3. 2 to the third power is 8. Okay, so that's how we can apply that question, and we can see that inverse relationship. So I believe I mentioned something about our bases. We have two special bases. We have what's called the common base, or the common logarithm with a base of 10, and the natural base. Now we've seen this before. Remember, e is approximately 2.7. Okay, so why is the common base 10? We've talked about the natural base before, but what about the common base? Well, think about the numbers that we count with. Okay, we count with the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we start back over. Then we use a combination of those numbers. So if we look at how many numbers, how many digits are there in the way that we count, well, we start at 0, that's our first digit. Then 1 is our second. 2, 3, 4 is our fifth. 5, 6, 7 is our eighth. 8 is our ninth, and 9 is our 10 digits. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If we take that 0 and we put it at the end, it's a little bit easier to see. There are 10 digits. And that is why base 10 is our common base. Okay, so when we have a base 10, the 10 turns invisible. Just like if I have 1x, I just write it as an x. There's an invisible 1 there. Or if I have 5, that's the same as 5 over 1, an invisible 1. Well, if I have just log of x, there's an invisible 10. Okay, so if I have log of 100, there's an invisible 10. And the question would be 10 to what power is 100? Well, what power do I have to raise 10 to in order to get 100? 10 to what is 100? 10 squared is 100, so the power is 2. So I can say log base 10 of 100 equals 2. Okay, and that means that our log base 10, or our common log, is the inverse of a base 10 exponential function. 10 to the x equals y. So we have this base 10 exponential function is the inverse, or the opposite of, the base 10 logarithmic function, which is called the common log, in which case we don't need to write that 10. So we can just write this as log of 100. There is a button on your calculator for common logs. Your calculator can, in one step, calculate any common log, as long as it's possible to calculate. Okay. The other I guess, special base that we have is the natural base. We've talked about this in previous chapters. When we're talking about the natural base, this is the base that appears a lot in calculations. And so E, called Euler's constant, is approximately 2.7. Okay, I don't know that I've told you it was called Euler's constant. Euler is the mathematician that this is named after, Leonhard Euler. A lot of people say Euler, but that's not the appropriate pronunciation of his name. And so just like pi, E is a constant. It has a value, it's not a variable. And so when we're looking at logarithms and we're looking at them as the inverse of our e to the x function, which we said was our exponential function. Remember, anytime you're graphing in Math Excel, the automatic base that it chooses is e, because that is our most commonly used exponential function. And so our base E, it has a very special role to play. So our base E logarithm also has a special role to play. Now, for a common log, the 10 just disappears. For the natural log, the E actually changes the notation of how we write the logarithm. So instead of writing log base E, we write ln. ln for natural log. Now, the notation comes from, I believe, Latin, and so logarithmic natural, okay, so ln. We don't say that it is a log natural of x, we say the natural log of x. So we would read this, the natural log of x, okay? Now, in class, as we're getting used to this notation, I'm not going to, dock points if you say log natural or anything like that. There's no repercussion for saying log natural, but that's not the appropriate way to say it. So that would be like learning a foreign language and then just disregarding some of the rules of that language, right? So we want to be careful about using the proper language when we can. Even though ln, we're going to say the natural log of x. Okay, so a calculation here, we could say the natural log of e. We're going to use one of those properties that we talked about on the 2 slides ago. The natural log of e, ln, is what tells me that the base here is e. So this is the same as log base e of e. And if the bases match, it cancels out. So our exponent here was 1. Okay, the other way that we can do this, now for natural logs, it's a little bit harder to use exact values, right? But if I had the natural log of e cubed, because the base is e, this becomes 3. Okay, now you can take natural logs of non-powers of e. I could take the natural log of 10, but that's not a calculation that I could do immediately in my head because I don't know e to what power is 10. It's not going to be an integer. It's going to be something with a decimal, and it's probably irrational. Okay, now your calculator can do that easily. There is a button for natural logs, which we'll practice in the practice in class, the classwork. Okay, so let's look at some properties for these two particular types of functions. So the basic properties of, and we're going to look at them together because I want you to see how they're actually the exact same properties that we've talked about before. Okay, so when we are looking at the common logarithms, log of 1 is 0 because 10 to the 0 is 1, right? Earlier we saw this as log base b of 1 is 0, but no matter what the base is, whether it's 10 or e, we have this same property. Okay, so that property holds up no matter which base it is. We have log of 10 equals 1, okay? And natural log of e equals 1. We actually just saw this in the example that I did on the previous slide. And that's the same as when we said log base b of b equals 1. So notice these are exactly the same properties we've already talked about. We're just applying them to the specific bases now. Okay, so this one here, if I have log base 10 of 10 to the y, the common log of 10 to the y, we can just read that as log of 10 to the y. I just said it 3 different ways. It was the exact same equation that I'm reading. Okay, and that must equal y. Same thing for the natural log. The natural log of e to the y must equal y because any log base b of b to the y must equal y. The bases essentially cancel out. Those bases matched, so they reduce each other. And then finally, we have 10 to the log of x that has an invisible base 10 equals x, and e to the natural log of e with an invisible base e equals x. And that's because any base raised to the log of that base of x must equal x. So again, we see this common bases reducing each other. Okay. Now, when I'm calculating these, if I was, for example, calculating log of 84, not something I could do in my head, I'm not going to write this. I'm not going to write my solution as log base 10 of 84, but while I'm doing the calculation, I can write the little 10 there just so that I can make sure to keep track of that base. Same thing for a natural log. If I were to write the natural log of 84, I would never write my answer as log base e of 84, but I can write the e to help me keep track of my work. Okay, so you can write those bases in your work, but your answer is never going to have a base 10 or a base e explicitly written in the solution for a logarithm because we have special notation for those logs. Okay, similarly to if I have an answer of 5x plus 2y minus 5 over 1, I would never write my answer like that. I would write it as 5x plus 2y minus 5, right? And I would always simplify this fraction. I would always simplify the log base 10 to just be log of 84. Okay. Our last example, or our last slide here, is an example of looking at these as transformations of graphs. So we want to, oh, sorry, there's one more example after this. So in this example, we want to solve this, this equation, and we're going to need to look at it in its exponential form in order to solve that. So remember, log of x is the same as log base 10 of x equals 4. And we need to know 10 to what power is x, and the power is 4. So it's a little bit weird to say it this way because my question isn't what it's equal. My question is this argument. I'm taking the logarithm of something, and I don't know what that something is. That x is trapped in the log. I can't divide by a logarithm. This is similar to if I had the square root of x. Right, I can't divide by a square root. The only way to get that x out of there is to change forms, to square the square root, right? To use the inverse in order to release the x. Well, here, in order to release the x, the inverse is exponential form. So I need to change this into exponential form. Change forms. So I have log base 10 of x equals 4. Those parentheses around the x are optional, but I find them to be helpful. So I circle the base. Step 1, identify the base. Step 2, draw a circle around the equal sign. Notice if I go this way, it's not going around the equal sign, right? So I don't want to go that way. I want to go around the equal sign. And then I say 10. I pass the 4 equals x. Now, how do I know to write that as an exponent and not to write it as log base 10 of 4 equals x? Well, this was already a logarithm, so I'm not converting it into another logarithm. I'm changing form. If it was a logarithm, now it will be exponential. If it was exponential, now it will be logarithmic. Now 10 to the 4th we know is 1 with 4 zeros after it, so x must be 10,000. Okay, so in this case, we didn't need a calculator to solve this. All we had to do was change forms from logarithms to exponential functions. Okay, there will be problems like that on the math Excel that we'll do as classwork. So we mentioned graphing. Okay, I mentioned graphing. To look at the graphs of a common log versus a natural log, Because the base has changed, it changes kind of the steepness of the function. Notice they'll still go through that critical point. That point is 1, 0. And that's because our exponential functions always went through exponential. We saw an anchor point at 0, 1. Right? That a lot of us said that in the exploration that you did. But if you didn't notice it there, we talked about it in class. So for a logarithm, X and Y switch. So if an exponential anchor point was 0, 1, then the logarithmic anchor point is 1, 0. So all of our logarithms, if they haven't been transformed, meaning adding, subtracting, multiplying, or dividing by a number, then it will go through that point 1, 0. So let's see if we can describe these transformations. From the natural log, notice it's the same parent function. Our parent function is the natural log of x. Just like for exponential functions, the parent function should have the same base. If I was converting from a natural log to a log base 10, that's not one of the transformations that we've talked about, okay? So the transformations that we've talked about, we need to have the same base for both functions, okay? And then we have to look at what has been added, subtracted, multiplied, or divided to our g of x. Now, I have a 2 here that doesn't have an x. The way that we're used to seeing this is the plus 2 after the function. So let's rewrite this. G of x equals -3 times the natural log of x plus 2. Okay, so I have that plus 2. I see the plus 2. I also see a multiplication by a negative and a 3. So multiplying by a -1, multiplying by 3, and adding by 2. Now, I also did that in the same order as if I were to substitute a value for x, I would take care of the parent function. And that tells me these are all going to be vertical transformations, right? If this was a horizontal transformation, it would have to be inside of the logarithm. The natural log of all of my horizontal transformations. And since nothing is happening inside of the argument, inside of the input for my natural log, all of these transformations will be vertical. So multiplying by -1 is a reflection. If I'm reflecting vertically, that is over the x-axis. Times 3 is greater than 1, so this is a vertical stretch. And plus 2 is a shift up by 2. Okay, so we start out with our natural log, which looks something like this. Remember, going through our anchor point of 1, 0. Then we reflect it. So now it's going like this, still through our anchor point of 1, 0. Then we stretch it vertically. So it's going to be even, well, let me try that again. Even taller and skinnier, stretched out vertically. So it still goes through the point 1, 0, but now it's 3 times as tall. And then it moves up by 2. So now I'm going to go 1, 2, something like this. Now it's not asymptotic to the y-axis. It will eventually pass. It's just going to take a long time to get there. And this is now 1, 2. Now, why doesn't it go through 1, 0 anymore? Remember, we called that the anchor point. Well, it doesn't go through 1, 0 because we moved it, we translated it up by 2. So our anchor point moved along with the graph of the logarithmic function. Okay, so this is our final sketch of the graph of g of x, starting with f of x as our parent function. Okay, now you can graph this in your calculator, absolutely, but you should still be able to visualize these transformations just like we were doing for our polynomial and our rational functions. Okay, That is the end of this section. We're going to practice this in class, but if you have any questions, feel free to email me. We do have a quiz coming up just as a check-in to make sure that we have a basic understanding of these three functions. So if you have questions on that, the quiz will be assigned next week. So make sure to set office hours before then.